Hello, everyone.
There we go.
So I'm going to be talking about Payjoin version 2. I've been working on Bitcoin privacy for a long time, and my belief is that we need privacy at all layers of the payment stack. If we're going to preserve it, anywhere we have leaks, those leaks will compound. So there's a little history behind Payjoin, which is it came about in around 2017 with this thing called Bust-a-Pay that turned into BIP 79 with some work from Blockstream and some people working on some online casinos. And then Nicholas Dorier and Andrew Camilleri from BTC Pay Server standardized it further so it could use HTTP for networking. So anyone with HTTP could pay join. Uh, and now I'm working on a new version where the receiver doesn't need to have a server because in PayJoin, the person sending the payment, the sender, and the person receiving the payment, the receiver, both combine their transaction inputs to get some privacy. So we're going to get into why we would want this. I gave you a lot of information right up front, why we need this new version, and what challenges an implementation is running into. So first off, what is PayJoin? The goal of this research today is more to elicit some review and feedback and discuss the current design of the coordination mechanism rather than the transaction structure of the pay join itself. So the idea of a pay join, why you would do it is because the Bitcoin blockchain is slow. Most people construct their transactions in a non-interactive way where one person contributes all of the inputs to a transaction. And because of that, anyone looking at the chain can make a lot of assumptions about all of those transactions on the network and how they're connected. And people's privacy is not preserved. If we're talking about strictly scaling and incentives, well, then PayJoin gives us the easiest way to make batches, which is the easiest way to scale a database. So this is how it works. And if anyone wants to interject in the middle of this, I welcome that. I like having sort of a discussion rather than strictly a presentation, but I'm happy to field questions at the end too. So your basic Bitcoin transaction has got three participants, where the network is, I guess, a bunch of participants, but you have a sender and a receiver. The receiver makes their destination address known to the sender, and then the sender has enough information to sign all of their inputs, create a transaction with a new output to the receiver's destination, and publish that to the network. This has some of the problems that I talked about before, where that assumption that a single person contributed all of the inputs is actually the sole open privacy problem Satoshi left in the white paper. So the transactions are costly because you only have one person's transaction intent, the sender, and the inputs belonging to the sender make privacy a big problem. So PayJoin version 1 tries to fix this. And the way version 1 works is by having a sender and receiver interact outside of the chain. We do this through partially signed Bitcoin transactions, which are PSBTs. The cool thing about PayJoin is it maintains the form of your typical transaction flow. So the receiver still generates some destination, which includes an address, but now also includes a HTTP endpoint, so a URL and this is all contained in a BIP21 URI. The BIP21 URI is supported by dozens of wallets across the space and makes it really easy for any wallet that can copy and paste, a payment request to parse what's going on and what payment methods they support or do not support. So these BIP21s contain the amount, a message, a label, perhaps a lightning invoice, and in this case, a Payjoin endpoint. So over HTTP, the sender can create a transaction as they would in the basic case from the address, sign it, finalize it, ready for sending to the network, but not send to the network. Instead of sending it to the network, they send a post request containing that PSBT to the receiver. Now the receiver has a choice. If the receiver wants to Payjoin, if they want to take the opportunity that the sender is giving them to consolidate some inputs or to transact on the fees of the sender, then they can add their inputs to the Payjoin. They can augment the outputs by the amount of their new input. So say the sender was paying them 2 Bitcoin and they already had 7 Bitcoin, they could add their 7 Bitcoin input and change the 2 Bitcoin output that was paying them to a 9 Bitcoin output, augment the basic PSBT that way, and then return it to the sender in an HTTP response. So now that the receiver has signed, the sender's signature has to be invalid because they augmented that original PSBT, and the sender would have signed using sig hash all, and so the receiver removes that signature. The sender has the Payjoin PSBT that has been augmented to either save money for the receiver or preserve privacy for the sender, and they can decide whether or not they want to sign this transaction based on whether that Payjoin PSBT is in their best interest. Assuming it is, and they sign, they then broadcast that to the network, creating a Payjoin. There are a few interesting restrictions on when the sender and the receiver sign here. So the sender sends a basic PSBT first so that the receiver always will get paid and the receiver will not expose any UTXOs from their wallet without knowing that they're going to get paid first. That way they can't be probed. And the sender has to broadcast because of this constraint that they go first because they need to have the updated PSBT. And this is all done over a single HTTP request and response. So in some ways, it's one shot. If it doesn't work on the first try, then the receiver will just broadcast the transaction they extract from the original PSBT or basic PSBT labeled here to get paid. But this does provide that opportunity to create a Payjoin to preserve privacy and save fees without disrupting the typical transaction flow. The sender just scans the destination and the endpoint, and the communication can happen abstractly behind the scenes. But in practice, this is hard to use. Many wallets have been able to implement the sender because it's only an HTTP client and some PSBT logic, which wallets are already familiar with. Lots of wallets use PSBTs. But the receiver has to run a server. So that server needs to get a static certificate in order to be able to augment the output. If the receiver wants to change that output from their original address, then they need some authentication. They need some way to communicate to the sender that it was actually them that changed the PSBT. And they can do that over Tor too. But they also want that encryption. They don't want to leak the original, the basic PSBT, or else the a third-party onlooker can have enough information to de-anonymize the Payjoin PSBT. Any privacy is lost if the intermediate steps get leaked. It's also synchronous. So the sender and the receiver, because it's a single HTTP request and response, they need to be online at the same time, which is a problem, especially for the receiver. Say they generate the address on their phone or on a desktop client and they send it over to the sender, then they might not be online when that sender tries to make a request. And if they're offline, the V1 protocol just fails. It just says it fails, and even that original PSBT doesn't get broadcast. Maybe the sender tries again to broadcast it on their own. And IP addresses also leak everywhere. Because this is a connection directly between the sender and the receiver, they figure out one another's IP address when they do this, which could reveal their information. JoinMarket did a great job of solving this static server problem by using Tor for their receiver, but that introduces a Tor dependency for everyone and depends on hidden services for discovery. So if a certain set of senders support Payjoin but doesn't support Tor, they won't be able to use the protocol. That's where Payjoin v2 comes in. Payjoin v2 introduces a directory, which is a store and forward server that can accept the PSBTs and forward them on behalf of either the sender and the receiver. So in this sequence diagram, a receiver first requests some subdirectory allocation on the directory. So an example would be I run the payjo.in server, where you can do this today using the Payjoin CLI tool. And then they'll use their public key to enroll at the directory. So now their destination in the BIP21 will include an address to make that basic PSBT and a payjo.in/ their public key. And anyone that tries to put things in that box at the public key will be able to communicate with the receiver. Then the protocol roughly proceeds as it would before, but instead of just one HTTP request, it uses polling. The receiver is listening on the directory and polls waiting for a request represented as a dotted line. The sender pushes their basic PSBT to that directory. As soon as it's available to the receiver, they're able to pull it, again, augment it with their input, return the Payjoin PSBT to the sender, and then send it to the network after the sender signs. But this is not the whole picture. So we had a few problems that are solved with this diagram. The synchronous nature of Payjoin is solved because we have polling with this always online directory server. So if the receiver goes offline and doesn't make this basic PSBT request until after it's posted, they'll still be able to do that as long as this subdirectory hasn't expired. Same thing for the sender. If the sender goes offline in between the time when the Payjoin PSBT is posted and sometime later, then they can just come online and check that directory, check that mailbox, get the Payjoin PSBT and continue the protocol. This gets rid of the need for certificates because this directory can always be online. This directory is a low resource Redis database, and these subdirectory locations that can take on the burden of getting a certificate so that the sender and the receiver can do all of this communication using only an HTTP client. We still haven't covered the IP address leaks, though. The IP address leaks, the network privacy, talking about blocking leaks at every layer of the stack, is done by something called oblivious HTTP. So the diagram above included, or in the previous slide, included a directory, which is actually two functions. It's actually an oblivious HTTP gateway and a Payjoin directory. The best way to think about oblivious HTTP, in my view, is that it's a solution that gives you 80% of the benefit of Tor with 20% of the effort. So instead of having a consensus network with exit nodes and many hops with relays, you just have a concrete 2-hop network where the client communicates directly with another server, an oblivious HTTP relay. These aren't run by the same person running the Payjoin directory. These are run by, right now, one is being run by Obscura VPN, and another is being run by the Bob Spaces incubator in Thailand. And they point to the Payjoin directory's oblivious HTTP gateway, which is at the same address as stated before, payjo.in. And anyone can run these servers. This is all open source code on the Payjoin organization and the Rust Payjoin repo on GitHub. So a client will encapsulate a request to the oblivious HTTP gateway using a key that the oblivious HTTP gateway distributes. So the relay can see the IP address of the client, but not the contents of the message, not the subdirectory that the client is trying to communicate with. Then it passes it to the oblivious HTTP gateway to pass it to the directory. So the directory can only see the contents of the message, but not the IP address of the client. And the protocol proceeds as in the prior document. Effectively, this is the sequence diagram, but there is a relay between the directory and the receiver and the sender and the directory, which is the oblivious HTTP relay. And as long as that does not collude with the directory, as long as the relay and the directory don't collude, then the clients can expect network privacy. They don't reveal their IPs. They don't connect their IPs to a particular PSBT or a particular sender and receiver pair without needing to have that heavy dependency of Tor. Of course, there is some cryptographic dependency. There's some keys that they need to get, which are akin to TLS certificates, but they're not exactly the same in that they can be distributed in slightly different ways depending on the constraints of the environment, which brings us to the ergonomics. How do we actually implement all this? So we use something called hybrid pub key encryption, which is, I suppose, similar to what Gordian envelope is trying to do in terms of protection. We don't use the envelope protocol right now to serialize the data that's inside the pub key encryption, but the sender and receiver exchange keys in the BIP21. You can see that that's the pub key in the subdirectory highlighted in red here. And that from that, they can use a Diffie-Hellman key exchange to establish end-to-end encryption and authenticated encryption without the use of TLS. So they can just use the server in the middle, even if it's not protected by HTTPS, to establish that end-to-end tunnel. They also establish an end-to-end tunnel with the gateway using this oblivious HTTP key, which can also be shared in the BIP21. And this can use SecP256K1, which is an unusual dependency outside the Bitcoin space. So that's something that needs some manual implementation, but is not impossible. And you notice that this oblivious HTTP key is in the BIP21. Where does that come from? So the receiver still needs to somehow get that information and may not get it through your typical certificate authority chain. So we need to figure out how to do that, especially in constrained environments like Bitcoin Core that don't necessarily have access to TLS. And then there's this question of encoding, whether or not we want to use here, these are Bec32M strings encoding both the public key for the subdirectory and the oblivious HTTP, what's called a key configuration, which includes the key material and which key derivation algorithm is going to be used, which hash algorithm, which curve, etc. But the spec uses hybrid pub key encryption for both of these, which is a new, it's an RFC 9180, I believe, or maybe that's for oblivious HTTP, but they both depend on hybrid pub key encryption so that this public key can be shared in the BIP21, and then a Diffie-Hellman key exchange can be used to establish the end-to-end encrypted connection. And the big bonus for this is that there's no TLS dependency, so it can be used in something like Bitcoin Core. There has been a draft to support SecP 256K1 as a curve for hybrid pub key encryption, but it's not totally standardized yet. But if we use SecP 256K1, then the hybrid pub key encryption standard already supports ChaCha20 Poly 1305 for authenticated encryption. And SHA 256 has a hash algorithm for key derivation. So we're not introducing any new cryptographic dependencies from your typical Bitcoin software because ChaCha is used in the V2 P2P protocol, so that from a dependency perspective, this becomes more palatable to include in various Bitcoin software. The encoding issue here is still an open concern, which is where I looked at a UR, and I think this is where Christopher wrote me an email on the Bitcoin Dev mailing list at first. So somehow we need to communicate these public keys. And at first I was using base64 URL, but there's a problem with base64 URL for encoding these keys, which is that it is case sensitive. And if it's case sensitive, then you can't encode these Bitcoin URIs in QR codes using the alphanumeric mode. So you end up with QR codes that are more pixels across, they're more dense, and they're harder to scan. So one option I thought at first was to use Bec32M because that's already supported anywhere that's encoding an address and it has the human readable part in the front to distinguish what's going on. So that's PK here and OH there. And it's everywhere. Yeah, UR seems to be more concerned with structured data, maybe something that has multiple fields, which the OHTTP key configuration does have, but it's already encoded in a structured binary blob from the RFC. So to me, it made some more sense to use Bec32M because that just encodes one binary piece and includes that human readable part at the beginning and a checksum at the end. But after iterating through this a few times, I found there was a bit bigger of an issue, which is that the equals sign and the question mark are not in the QR alphanumeric encoding set. It's just like a base 45 set. So these URIs are not eligible for encoding like that. So I went to the Bitcoin design community and discovered that they can actually be encoded in mixed mode, which is some parts of the string that you're encoding can be encoded in binary mode, some parts can be in alphanumeric mode, but in practice, it seems like only the last part, at least in software that does this automatically, only the last part will be encoded using that alphanumeric mode, and the savings as a BIP21 get larger in the size of a QR are marginal. So I'm still not sure if it's which encoding makes the most sense for this, and that's something I'm hoping for some feedback on. I think it's very important to maintain the BIP21 for the Payjoin requests because it's already supported in dozens of apps. Like I said, Cash App uses this, Foundation uses this, Sparrow uses this. It's totally backwards compatible with the V1 Payjoin because this store and forward server can have a V1 adapter so that when a V1 sender tries to make a Payjoin to a receiver using a V2 uh, receiver at that directory, if the V2 receiver is online, they're able to respond immediately. Their polling gets a response right away, and they produce a reply right away within a typical HTTP request response timeout window and still make that page join happen. The other important thing to me is that just ergonomically, we want these things to happen automatically in the background. Bitcoin privacy solutions in the past tend to be focused on this idea of a separate mixing step where you manually go in and make a batch transaction with other people. And that costs more money on top of your typical payment flow. And it creates an overt signature on the blockchain that you're using some privacy protocol. And then you still need to manage your change afterward. So it costs you time and money, and the privacy can be tenuous you get from that. So having it happen at the time of payment seems like a hard requirement for me for a privacy protocol that's going to be widespread. And lastly, this encoding consideration is sort of the last real dependency specification thing to figure out before we roll this out. So there are two pieces of software that run this right now. There's the Bitcoin D Payjoin CLI client you can run on top of your Bitcoin Core instance to send and receive Payjoins. Like I said, the directory is open and running, as are the Payjoin relays. Um, and getting the envelope right for even alpha release is somewhat important because once people have this software out in the wild, they may not want to change it and make their previous versions of their software incompatible. That is what I have for a presentation. So the BIP 77 on the BIPs repo, the PR is 1483. I'm really hoping to get some feedback in the design of this from a coordination perspective. The transaction structure is a different but related question that I haven't totally covered here because there's not much that a new coordination mechanism can change in the transaction structure. But the big idea, I think, to understand about transaction structure is that there are two types of privacy we're trying to preserve. We're trying to preserve third-person privacy. So if Christopher and Wolf are transacting, I shouldn't be able to look at their transaction and figure out who paid who. I shouldn't be able to figure out how much money was exchanged between them. Maybe I know that they communicated, but they should have some privacy from me. That's the kind of privacy that Payjoin typically gives you, and uh, because the transaction it typically produces looks like other transactions that have multiple inputs that all came from one person. So you have some indistinguishability by default. There's also a question of second person privacy. So if Christopher sends Wolf money, it would be best if Christopher didn't know what outputs that Bitcoin ended up in, and for Wolf not to know where that money came from, which inputs. And we can do that with potentially a Payjoin protocol involving more than two people, which is something I think could be coordinated in the future. And to do something like that, we definitely need to have the basic case of two people down. But I think we still want to preserve this sort of BIP21 payment flow that people are comfortable with now, where they scan a QR code or they copy and paste a URI, or hopefully increasingly they just tap and this is exchanged over NFC. So yeah, that's Payjoin V2. Thank you very much, and I hope I can answer any questions you have.
Thank you. So let's leave your slides up for a moment. So I wanted to chat with you about a few different things. Wolf and Shannon also may have some questions or contributions. So I think we'll sort of start at the end point. You've encountered the exact problems that we had with encoding of things and the problems that it causes with the QRs. And we do have a library that does do the multiple, tries to do the smart thing. Wolf, what are the two I know one, what are the two QR libraries you did that do the fancy QR encoding?
Yeah, we have a QR encoder library, which I based on I think it was a C++ library that I converted to Swift actually. But it basically allows the basic QR encoding API available in iOS does not allow the mixed mode encoding that Dan was referring to. Whereas this one does. You can encode fragments of a QR code in binary and other parts using there are other encoding modes that are more compact for certain kinds of data. But we found that the support for those, while it's useful to support that for certain kinds of pre-existing formats that we can't control, we also realized as we were experimenting with various kind of things, the exact same things he was running to, for example, question mark and equal sign not being in the basic alphanumeric mode of QR codes, and that was why the basic alphanumeric mode was widely supported for as just a single fragment in a homogeneous QR code. So
we also found problems. I mean, we did one from JavaScript in Swift, but then other people needed it in C, and then other people wanted it in Rust, and it was hard to get people to support it. In the end, we basically said this isn't the right answer, so we came up with the UR format that you're familiar with, which addressed all of these different types of problems, but also allowed us to leverage CBOR as an option for tagging things. That doesn't mean, I mean, when we CBOR tag a PSBT, the PSBT is not actually completely converted to CBOR. All of its structures are intact. We do a little bit of magic in there so that we can separate the pub keys out to make it to optimize it, which has gone through a couple of iterations. But that is now well supported. There are over 13 wallets that support it, and in particular of the ones you mentioned, I think Foundation Devices would have been here today. They're very actively supporting our URQR and envelope work. And I think Sparrow has also been doing libraries and things of that nature here. So I think there's less dependency problems than you might think. I think the harder problem is that we have a richer stack for good reasons, and every one of those deserves maybe a BIP. And the BIP process has been a bit challenging for some of this stuff. So we'll see how
there's
that
a couple more contributions I'd like to make about that too, about UR, if I may. So if you have a pre-existing binary structure like a PSBT that you want to handle as a UR, The only thing you need to do is assign a CBOR tag and a UR type, which is a short human readable string, to that, and then you just take your binary structure as a CBOR binary string, you wrap it in your tag, and then you have a standalone CBOR structure that is a binary structure. If you want to encode that as a UR, then you exchange the tag for the UR type, and you just basically use the byte words encoding for that, and the UR type is isomorphic with the tags, so you can go back and forth between those things. And there's a couple of advantages to this. So first of all, you don't have to redesign your binary structure in CBOR, especially like in the case of PSBT. There's already a lot of software that supports parsing and writing of PSBTs. PSBT is also a semi-fluid format. It may still change in the future, and so there's no reason to track that with a separate CBOR specific structure. The other thing is that, though, when you're dealing with QR codes, which is one of your interesting use cases, is that because URs are deliberately designed to only use characters from the alphanumeric encoding mode, and because it's case insensitive, so you translate to uppercase and you have something that's perfectly suitable, in fact, more compact than base64 for the purpose of QR codes, that we also support multi-part UR format, which is where you can essentially break your message of arbitrary length up into a series of parts, which are rateless fountain codes, which can be transmitted in basically an infinite stream of changing codes that mix various parts of codes of your message together. And what this does is this allows readers to essentially scan this animating QR code and converge upon the final message, rather than there's some other schemes proposed which don't use the fountain codes, which if you miss a message more than once, you have to wait for the entire cycle of codes to repeat over and over again. And so you can actually diverge in terms of from optimal transmission time, whereas rateless fountain codes tend to converge. So if your message is larger than can be comfortably represented in a moderate QR code of moderate density, depending on your camera resolution and your screen resolution, things like that, then you can use this extension of the UR format to transmit messages of any length. So that really ceases to be a concern of fitting it all in one QR code.
Yeah. So, I mean, a couple of different things to note there. We have examples of it being used on very constrained hardware, both on the display side. Lethe Kit has a 200 by 200 display, so it's a very, very small QR to start off with, and it the tooling will properly size the QR and display it there. But also on the input side, very tolerant of very different scenarios as far as the quality of the input device, et cetera. I found, for instance, I think Sparrow is in kind of the worst case in some cases because it runs on laptops with very poor cameras or don't focus well, et cetera. And it's taken a little while to find the right, match of sizes, but I think we've got some really good answers as for, what is the optimum there, and that's been very reliable. So that's one part of your thing. I think some other aspects of stuff is that, we're going to talk about in the next presentation a little bit about, we really feel like the future of the world is going to be multi-sig. And so we also have these coordinator issues, which are also dealing with PSBTs and may not, necessarily be fully, trusted with any keys at all. They may purely do a coordinator function. I think there are also a lot of security properties around devices that are functionally separate. So you might have a phone that talks to an NFC card that then talks to a separate device, which actually does the display. So we have a lot of these different things that in order to increase security, we're having to do much more complex things, and we're reaching the level of user tolerance for these that is low. So, we published a scenario for, say, foundation devices, 2 years ago with, that really, no single point of failure, multiple devices, heterogeneity, all the Gordian principles, et cetera, but, just didn't, wasn't adopted because it was just too hard. And I see this as going to be increasing future with all of all of the Bitcoin protocols. We're all going to be, hitting up against these. And I think Gordian envelope, and URs addresses a lot of these in ways that are transport agnostic. We don't care if it's oblivious HTTP or Tor or, the Whisper protocol. It doesn't, or iMessage if you really want to. So we really want something that can transport anywhere. So the latest stuff, which is what we're going to talk about in the next presentation, is request response, and that allows for some continuity of a larger number of transactions that are happening, and allows you to maybe wrap those inside request response things that basically can establish keys between two parties. So you have multiple parties in your protocol, in your swim lanes, that need to get keys in a variety of ways. And in many cases, a trust on first use could make a big difference. Like, okay, this is now the second time somebody's requested this, but something's changed. I don't want to deal with you anymore because, you're not necessarily, who you were before. And I think there's a lot of cases where trust on first use are powerful, but obviously, that's just the simplest of a number of cases where you establish trust through various other channels for more complex or more concerning issues, and you need to have the privacy that we are all seeking with these protocols. So I'm hoping that with the wallet community that is already involved with the Gordian stack that we've built, that we can future-proof for these much more complex things. Shannon, do you want to? You're going to be talking in a few minutes, but is there anything that isn't in your talk that you want to connect to the Payjoin discussion?
Oh, I just generally what I'm going to be talking about is request response, which is an envelope functionality that allows one person to say, hey, give me something, and then the other party to give whatever's requested or respond in some other way. So I think there's, a question there of, hey, is this something that might be helpful for the overall protocol, since there's so much back and forth if you're already going in for URs, for example, and for a penny and for a pound. But I think that's going to be the main thing to maybe think about. And it could be you're well too along in the Payjoin to even think about reworking that. But I'd say think about that as an option when we're doing the other presentation.
I'm definitely here because I'm thinking of these things as an option. The biggest question I have about the applicability of UR is with regard to the BIP21 flow. So a lot of the working around Payjoin v2 has been to support or be backwards compatible with the way that so many wallets already exchange this request information. And it seems to me like this was the thing that was both addressed by that original message from Christopher on Bitcoin Dev 6 months or a year ago, probably 8 months ago. And it's also, I'm not sure if it could be replaced by UR. So at first, these public keys were base64, and they weren't even base64 URI encoded or URL encoded, which is wrong. They definitely need to be URL encoded. But I'm not sure how these components can be replaced by UR, because it seems like it would break the BIP21 destination flow. When it comes to the pub key encryption, like what's getting sent during the automatic part of the protocol, that could work. You could encode those things with CBOR, but here, how do you think that applies?
Yeah, I mean, so I don't know how to necessarily retain compatibility with BIP21. And that's been a concern. There are a number of other things. I mean, the good news is that, even, this doesn't actually contain a PSBT. So,
Right.
it's, that was the thing that drove most of the wallet companies to the, QR/UR stuff, was we just were very quickly hitting the limits of what was possible in a single QR code. Um, and you're not facing that right now, so it's not urgent for you. That being said, when I start thinking about multi-sig, there's some extra information I want to be able to put in here so that, because at the other side, it may require multiple devices to agree maybe with the Frost protocol or things of that nature. And there's no expandability here. So, my intuition says, start in the back end of this stack, having a more request response envelope UR style of encoding all of this stuff, support the BIP21 as the lowest case, but you've got already, with at least like Sparrow and Foundation Devices and some of the other parties that are already doing the current PSBT format. I think you could reach some level of critical mass where you have it's a BIP21 plus switch. It's like, okay, you can, if you want to support the legacy, we'll still support the legacy. But you really should, use a more modern wallet that can do the better encoding and initiate much more complex kinds of interactions. One of my other challenges here also is the whole question of you're doing this with a remote party, who and you're also having to trust these third parties. There's no persistence in this particular trust things. So I think there's some questions of, you know, uh, uh, again, trust on first use. Something's changed. I mean, we've
Can we
certainly
explore those questions before we move on? What questions do you have about persistence or the kind of attacks that these third parties could leverage?
Well, I think that the question is that the I mean, I'd have to look at, some of the exact details there, but
Yeah.
you are relying on a third party to begin to do these types of things. So if, one or more of these becomes compromised, or, a DNS attack or something of that nature where it gets pointed to somebody else, and the ability for the system to detect there is now somebody who's taken over this particular service, and is, logging more IP and doing more correlation of various behaviors on the on the internet. I don't know how you tell easily. Especially if we're trying to avoid going through a certificate infrastructure and things of that nature, it becomes much more important for the parties to, to be able to kind of pin keys themselves rather than relying on a third party to pin for them.
Oh yeah, I think I actually I skipped the bootstrapping slide, which is like how do you get the key for the gateway? And we do depend on TLS, and then if you're using some other infrastructure, like if you're using a cache, I
Yeah.
think that does become a problem. Yeah, but for all of the current implementations, HTTPS is still available, so
Yeah.
that hasn't become a problem yet. But yeah, I do see that problem.
But as long as you're doing HTTPS, now you've got IP addresses, you've got other also, interesting kind of tracking around, through DNS. So you also have to do DNS through HTTPS, and I mean, you just have this whole stack of security hacks to a certain extent. I mean, I'm the I'm the co-author of TLS 1.0, so I've been watching these hacks over the years. And to a certain extent, we can rely on them because big companies rely on them, but that also means the bigger adversaries can take advantage of them. So, I'd like to not have to use that as a choice. I think, we're approaching the point with some of the envelope stuff where we can avoid all that and just not have to worry about that because, we're going to be self-sovereign and responsible for that ourselves, or at least, the vendors of the wallets that, are creating tools for us rather than relying on infrastructure vendors who may not care as much about Bitcoin privacy as our wallet vendor does. But it's, I'm not saying that any of this, I mean, I think that, BIP21, your current HTTP bootstrapping, the oblivious HTTP, et cetera, are all good, innovative improvements. It certainly would be a useful step forward. I would just love it to be able to future-proof a little bit for some of these larger problems by, slipping in a little bit of additional capabilities. And, we can talk more about that. I wish the Foundation Devices people were here because I know they've implemented V1. They may have some ideas around V2, and they've been working, closely with Wolf on some of the request response stuff. So, Wolf, do you want to say anything more before we go to Shannon's presentation?
No, I don't think I have much to add. I think I'd be happy to sit down with you, Dan, and just kind of talk through, your scenarios in detail and kind of see where it might fit in. I think it is important to say that, we've designed our stack so that you can pick and choose depending on your use cases. And, I mean, UR is, a high level format for, essentially translating any binary structure to a very limited subset of ASCII for ideally, for handling as a URI or transmission QR codes as multi-part. But if you don't need that for some reason, then you don't need it. And if you have, like I said, an existing structure that you just want to wrap in that, you can do that very easily. So you don't need to necessarily design a set of CBOR structures from the ground up, but there are some advantages to doing that as well. And so our stack is
like we did with HTTPS, where it was useful to extract out the pub keys. So we have a CBOR structure that uses the PSBT format as is, including as it evolves in the future. It just simply has little placeholders for all of the pub keys because those pub keys are useful.
I should think you're referring to output descriptors, actually.
Right. You're correct. You're correct. It's output descriptors. We haven't done that with PSBT, but it's been discussed. That's right. And then, of course, this particular slide that you're talking about here, this is something we're working on right now. We hope to have, available this, this summer is, how do we establish, a root of trust with one of our collaborative key recovery servers. So we've had some previous presentations about, you want, hey, server, will you store my secret shares for me? Okay, later, please give me, I need to update those secret shares, or I need them back in some fashion, and I've lost my keys, and I need to reestablish authentication with you. We've been working with multiple companies and parties to kind of establish that. And one of the things that will emerge will be a subset of that is useful for lots of other apps besides collaborative key recovery, because that's the way we design things. And I think it might help you with this as an alternative. I'm not saying you've already got this working. I'm not saying don't support this, but it could be that it becomes an alternative format.
This is definitely the biggest hack of the whole operation, which is I think how I managed to skip it, even not thinking, because it uses TLS to bootstrap. And if there were a robust technology elsewhere, I would absolutely consider that and be willing to, I mean, I am willing to sit down and hash this out more. I appreciate you guys having me and being able to do this today.
Great. Well, thank you very much.